Hello, stats friends. All right, so now we're kind of smack dab in the middle of our chapter on sampling distributions, and we're going to investigate further the idea of sample proportions, and we're going to dig into what it means to have a difference in sample proportions. So this lesson is going to be broken up into 2 days. The first part is going to be all about how to calculate the mean and standard deviation of a sampling distribution of a sample proportion, which we call p hat. And then in day 2, we're going to calculate the mean and standard deviation of a sampling distribution of the difference in sample proportions, p hat, p hat 1 minus p hat 2. So if you're looking for day 1, day 2, that's kind of the split. All right, so starting with, remember our vocab here is really important. We have a sampling distribution of the sample proportion p hat. It describes all the possible, it's the distribution of all the values taken by the sample proportion p hat and all possible samples of the same size. I cannot talk today. That is not a good lesson to not be able to talk. All right, so here's an example of a sampling distribution of the sample proportions, and they're referring to the example about the pennies. Hopefully in class we've had a chance to kind of investigate this premise, but pennies from the 2000s, and they're taking samples of size 20. So this particular distribution has 50 samples of size 20. So notice the distribution. By the end of this section, we should be able to kind of anticipate the shape, center, and variability of distributions simply based on some information that we know. So here there's a nice little view of some side-by-side distributions. So if we kind of notice the difference here, these top ones in this top row, their sample size, 25, 25, 25. Comparatively, when you look below in the bottom row, the sample size has bumped up to 100. So now let's kind of figure out what's the difference between them. So a proportion of 0.1, whether it's a sample size of 25 or 100, you might notice something that you can say about this graph. Now notice when there's a larger sample size, we have less variability, which we kind of knew from the last section. So we're going to start to make some connections here. Now you might notice these guys in the middle, they have sample proportion values of 0.5. I'm sorry, excuse me, population proportion values of 0.5. And then if you compare that to what's on the left side and what's on the right side, that's kind of cute that they did it this way. You see some skewedness. You know, this guy is skewed to the right, this guy is skewed to the left. So maybe that has something to do with the value of P. Let's find out. So when n is small and P is close to 0, the sampling distribution of P hat is going to be skewed to the right. So we're going to have the skewedness when the sample size is small. We're going to see some variability in a moment too, but notice the P is small as well. Man, this is just such an exciting moment. As your teacher, I'm kind of thinking ahead to the next chapter, and I'm like, oh man, it's going to get good. All right, so let's continue to talk about shape. When n is small, but the p hat value is close to 1, so you got a bigger p hat value, you're going to have this skewed to the left business. And then finally, we notice that the sampling distribution of p hat becomes more and more normal when the value of p is closer to 0.5 or n is larger, or even better, both. So if I kind of go back and look at that, notice how the skewedness was more distinct when we had a smaller size of n versus a larger n. So it had more of a normal distribution shape, but it took care of the variability. That was nice. But notice here in the middle, this bottom row, this is where we had a larger size for n and a p-value that was exactly 0.5 for the population proportion. That's a pretty graph. All right, I lost my place. Where are we at here? Center. Yep, that's where we're at. So center says when the mean of the sampling distribution of p hat is equal to the population proportion. Cool. This makes sense because the sample proportion p hat should be an unbiased estimator of the value of p. So what we're going to find out today is when I ask you for mean, you don't really have to second guess or calculate anything. It's going to be the value of p from the population. The variability, which I've kind of already spilled the beans on, but we've noticed that for specific sample sizes, the standard deviation is larger for values that are p that are close to 0.5 and smaller for values that are close to 0 or 1. So when they held the sample size the same, they're referring to the size of the standard deviation and the variability in that example. So here, let's see, where is I at? Wow. Okay. I got a lot of cute color-coded slides. Here we go. For specific values of p, the standard deviation gets smaller as n gets larger. And we kind of talked about that in the last lesson, where we're going to decrease the variability if we have larger sample size, which we learned last lesson increases our, okay, get it right, Abruzzo, our accuracy, right? Not precision, but accuracy. Now, specifically, they do mention that if you were to multiply the sample size by 4, that's going to cut the standard deviation in half. So when we're trying to figure out like what kind of a sample size should I be aiming for, and we're trying to adjust that later on, that's something to keep in mind. You can actually half the standard deviation size if you were just simply multiply the sample size by 4. Now I say simply, but that's not really a simple thing to do always. All right, let's keep going. This is going to have a bunch of info on it. So sampling distribution of sample proportion p hat. Choose an SRS of size n from population of size capital N. So watch the notation there with proportion of p successes. Now, right away, I think something should be firing off in your brain like successes. We've talked about this before. The binomial distribution is going to have, you're going to have some things kind of firing off going, oh my gosh, I think we talked about this before. Yes, this is a great moment in stats where things are going to start to come together. So hang with me. So the mean of the sampling distribution for p hat is the value of p from the population, the proportion of success. The standard deviation is calculated by, and then I'm going to start calling these successes and failures because that's going to kind of help us later, but it's the square root of success times failure divided by n. Now, this formula can only be used if something called the 10% condition is satisfied. So basically it says that your sample size has to be less than or equal to 10% of the entire population. So your sample size can't be so large that it's going to screw up your formula, basically. Now, this has always bothered me, even as a student, it bothered me because I'm like, well, what if I don't know the sample size or the population size? Well, do your best estimate. I mean, a lot of these problems coming up are like, of all of the students in a large high school. Well, that's a very like generic description. A large high school to me might mean something very different to a kid who lives in like central Illinois where their large high school has 40 kids in it, in a grade. So again, use your best judgment. The whole point is on an AP exam, you just mention that you've satisfied the 10% condition by showing some math and then you're covered. We'll talk more about that later. All right, the value for standard deviation of p hat measures the typical distance between the sample proportion p hat and the population proportion p. This typical distance business, this is going to keep coming up every time we go to answer these variability questions. All right, there's another thing we got to satisfy. It's called the large counts condition. So the sampling distribution of p hat is approximately normal as long as the large counts condition is satisfied. So we got this 10% condition that allows us to use this formula for standard deviation. And then we have something called the large counts condition that allows us to use an approximately normal distribution so we can use like our z-scores and our normal CDF stuff. Now, this formula is interesting. It says n times p is greater than or equal to 10. Well, if this is proportion of success and n is the number of, in the sample, basically it's saying you have to have at least 10 successes, and then here would be failure, right? So you have to have at least 10 failures. Okay. And again, that's a really vague, like, how do I know? Well, you're going to figure it out. You're going to be able to calculate it. All right. So the two conditions mentioned in the preceding slide, those are very important. And this is going to come up a lot in the AP exams. So the large counts condition says if we assume that the sampling distribution of p hat is approximately normal, when it isn't, that means that any calculations we make using the normal distribution is actually flawed and we've done the wrong kind of math. So the 10% condition says when we sample with replacement, the standard deviation of the sampling distribution of p hat is exactly that. When we sample without replacement, the observations are not independent. So like you're going to change the probability of like pulling out a winner essentially if you don't replace what you're taking from. And the actual standard deviation of the sampling distribution is smaller than the given by the formula here. So what they're saying, and this is not, this is kind of above our pay grade, guys, because some very smart statisticians in the past figured this out. It says if the sample size is less than 10% of the population, however, the value of the formula is pretty darn close to correct. So even though we know we're going to be sampling without replacement because we're, taking them out and figuring out the data, as long as our sample size is small enough, less than 10% of the less than or equal to 10% of the population size, we're allowed to kind of cheat. That's not the right word, but we're going to fudge it a little and we're going to use this formula, even though it's technically not the right formula. But it sure does make our math simpler. All right, so here we have a nice problem. It says, suppose that 84% of students at a large high school regularly use a backpack to carry their books. This is groundbreaking stuff, guys. We took a SRS of 100 students, and we're calculating p hat to be the proportion of students in the sample who regularly use a backpack. So first question, identify the mean of the sampling distribution. So the mean of the sampling distribution is equal to the value of p from the overall population. So the probability of success, if you want to think of it that way, so 0.84. For oops, I skipped a little. So part B says calculate and interpret the standard deviation of the sampling distribution of p hat. Now, a little note here, verify that the 10% condition is met. So the first thing we have to do is verify the 10% condition. So this is cute. They said, assuming that n equals 100 students is less than 10% of the students at this large high school. So they didn't really verify it because we don't know how many students are at the high school. So we're just going to put a little blurb, a cautionary blurb in that says, I'm assuming that this is, less than or equal to 10%. That cracks me up. By the way, at our high school at Harlem, let's see, how many students do we have here, guys? About 2,000. 2,000. So this would satisfy the 10% rule at our particular high school. Now, do you have to get real specific like that on an AP exam? I would hope they would give you more information so you could verify it easily. All right, so because we met the 10% condition, we can now move on and we can calculate the standard deviation and then interpret it. So the calculation of the standard deviation says the square root of success times failure, so the complement is failure, right? Divided by the sample size of 100, and it comes out to 0.0367. So here's the interpretation, and you're going to want to highlight some words here because this is like a plug and play. You're going to have this template for how do you always answer these questions. So in simple random samples of size 100, so that 100 could be wiped out with whatever your normal problem is, your next problem, I should say. The sample proportion of, and then again, students is from this problem, but it might be something else in another problem, of students who regularly use a backpack, so that part would be, for this problem. This is the part that's never going to change. Will typically vary by, and then here, this will change 0.0367 from the true proportion of, always the same, and then we write in whatever the true proportion is. So if I had to make a little template for myself, I would say in simple random sample size of blank, the sample proportion of blank will typically vary by about blank from the true proportion of blank. Very helpful, Mrs. Abruzzo. Thank you. All right. Oops. Can't sneak peek yet. Part C. Describe the shape of the sampling distribution of p hat and justify your answer. Now, without actually looking at the distribution, we should be able to kind of figure out some stuff. So the first thing we have to do is see if the large counts thing is satisfied before we talk about the shape. So the large counts says n times p has to be greater than or equal to 10, and n times, my old school teacher book used to use Q for failure, but 1 minus p works too. So we're going to have 84 successes according to this, and in a sample we should have 16 failures. Now, because 84 and 16 are both greater than or equal to 10, that allows us to approximate using the normal distribution. So we say the sampling distribution of p hat is approximately normal. And that's all they wanted from me on that question. All right, so here, oh boy, suppose that 75% of young adult internet users from 18 to 29 watch online videos. I feel like that's a very low end number. A polling organization contacts an contacts an SRS of 1,000 young adult internet users. So there we go. And calculates the proportion p hat in this sample who watch online videos. So we have, this is our p-value, right? And then this is our sample size n. So they're going to have you do a whole bunch of stuff here. So in a minute, you're going to pause the video, but you're going to tell me what the mean is. You're going to calculate and interpret the standard deviation. Make sure that you check the 10% condition first. And then, is it normal? You're going to have to check the large counts condition. And then if a sample size were 9,000 rather than 1,000, how would this change the sampling distribution of p hat? So if you're not sure how to answer that last question, play around with it a little bit and see what happens. I'm going to pause the video. You are going to pause the video because I'm going to show you the answers right now. All right, so first question, the mean is 0.75. So the value of P from the overall data here, 75%, that's the mean for the distribution. So the 10% condition, 10% of 1,000 is, okay, no, I'm doing this goofy. There are more than 10,000 young adult internet users. Yeah, pretty certain there's more than 10,000 people who are in that age bracket who use the internet. That was kind of a weird way for them to say it. So anywho, basically what they did is they just took the sample size, multiplied it by 10, and said, is there at least this many out there? And the answer is yes. So that validates that 10% condition. It has been met. So because of that, we can use our standard deviation formula of square root of success times failure divided by n. So 0.75 times 0.25 divided by 1,000 comes out to 0.0137. Now we have to interpret it. So this is where that little template comes into play. In simple random samples of size 1,000, the sample proportion of young adult internet users that watch online videos will typically vary by about that number from the true proportion of there. So remember the pieces that are unique to this problem, size 1,000, and then young adult internet users that watch online videos. There's the context. There's your standard deviation, and then here's the true proportion. I feel a poster in our future, huh? All right, so for part 3, we had to figure out the large counts condition and make sure it was, I'm sorry, the 10%. Abruzzo, come on, large counts condition. Thank you. I keep calling it the wrong thing. So n times p and n times q, or failure, have to both be greater than or equal to 10. Well, we're going to have, in a sample, we're going to have 750 successes, according to our data, and 250 failures, which is surely they're both greater than 10. So that allows us to say that the distribution is approximately normal. And then in the third question, when they asked about what would happen if you up the sample size to 9,000, well, it would still be approximately normal because when you did 9,000 times these guys, you definitely have more than 10. And the mean would still be 0.75. However, your standard deviation of the sampling distribution is going to be smaller. In fact, they went and calculated it. And it even went as far as to say by a factor of 3. And if you're like, where did they get the 3 from? Well, they're showing you here it's the square root of 9 because remember the formula is square rooted. So if you take this denominator and you bumped it up by a factor of 9, but then you square rooted it, your overall statistic is only up by 3 times 3. Don't get hung up on that part of the math, guys. The idea is, hey, look what happened. We increased our sample size and we got much less variability, which is what we knew would happen. All right. So using the normal approximation for p hat, when the sample size is large enough, I feel like I put that problem in the wrong spot. Oh, well. So it's large enough for n times p and n times, I'm going to call it q, but n times 1 minus p, to be both at least 10, the sampling distribution of p hat is approximately normal. Yeah, okay. So in that case, we can use a normal distribution to estimate the probability of getting a specific, obtaining an SRS in which p hat lies in a specific interval. So this feels a lot like something we did back in the day. All right, so this time we have a polling organization asked a simple random sample of 1,500 first-year college students. So there's your N. Suppose that 35%, oh, I should finish the question. College students, how far away from away their home is. Suppose that 35% of all first-year students attend college within 50 miles of home. So they're going to be calling this the p-value, just heads up. So find the probability that a random sample of 1500 will give a result within 2 percentage points of the true value. This, my friends, they're going to want us to look at this as a normal distribution question. Now, we know the value for the mean is 0.35 as given. And then this is that cute little assuming that 1500 is smaller than 10% of all of the first year college students. Now, do we know that for a fact? No, but we're just going to say it. That allows us to use the standard deviation formula and get 0.0123. So what we can do now is we can create a normal distribution, and it's important that you draw it with mean in the middle, and then you're counting up your deviations and down your deviations. Okay. Now the next, oh, I skipped this part, Abruzzo, you shouldn't have done that. Before we went ahead and drew the normal distribution, we should have done the large counts condition to make sure that even was considered to be normally distributed or approximately normally distributed. So n times p, we're going to have 525 quote successes, and then n times 1 minus p is 975 supposed failures. Again, failure is a strong word here, but that's okay. That's what I'm calling it. So we are able to use the normal distribution calculations because it's approximately normal. All right, now this is where you get to decide which direction you want to go. So we know we can find the probability between these two marks on the normal distribution by using z-scores and our table A in our book. You know Mrs. Abruzzo doesn't like that, so I'm probably not going to. I'm going to use technology. And frankly, I'm not going to use this method of technology because I would have had to standardize. For this particular problem, I wouldn't bother. I would have done that. So, oh, I forgot to mention something, and I apologize. Where did these 0.33 and these 0.37 come from? Well, remember, the question was within 2 percentage points of the true value. So 35% is the mean, but if I go up and down 2%, that takes me to 33 and 37%. So that's where they're coming up with these endpoints to the interval. I apologize, I skipped over that. So either way, you're going to get a probability value of about, almost 90%. There we go. So there's benefits and drawbacks to all the methods. For me, it's just kind of what comes more naturally to me. I want to be well versed in all the methods just in case I have to use one versus the other because you never know what kind of kooky thing they're going to ask on the AP test. All right. Oh, P.S. Remember, if you're doing this, you have to claim your lower, your upper, your mean, and your standard deviation very explicitly, not just the command. Don't give me calculator script. You got to tell me what everything is. All right, so that would be the end of day one, if anyone's looking for that. That was the end of day one. So now we're going to look at what's going on in day two. What if we have sampling distribution of a difference between two proportions? So here we have two high schools, and we have high school one and high school two. At high school one, 70% of the students did their homework last night, so their value of, their P value, if you want to call it that, is 0.7. And then the other school, only 50%. So their value for P is 0.5. Now notice they're differentiating between them by calling them P1 and P2. Also notice this is not P hat, right? This is the overall population data. So a counselor at school one selects a simple random sample of 100 students and records that proportion, and they're going to call it P hat 1. High school two's counselor did the same thing. They have 200 students in their sample. Either way, they're calling their proportion P hat 2. So here's all the information with all the variables that they're using to define it. So we have two populations, two parameters, two statistics that are based off the parameters, and two sample sizes. Wow, that's a lot of math. All right, here's what's going on. First thing, they wanted to check that they could use the normal distribution, so they checked the shape by doing the large counts condition. So for school one, that was 100 times 0.7, which is greater than 10, so check. And then 100 times 30, 0.30, which is 30, which is greater than 10. So this shape was approximately normal. The mean for their, sampling distribution of their proportion was equal to 0.7. And then when they went and used they should have done this first. They checked the 10% rule and it's saying 100 must be less than 10% of all the students at school one. I don't know how they know that. They're just saying it must be. So that allowed them to use this calculation to find standard deviation. So here's all of the statistics we need. And I shouldn't call them their parent. Well, okay, I'm going to confuse myself. I'm going to stop talking. Moving on to school 2. Large counts condition is satisfied. The mean is 0.5. Standard deviation is able to be calculated because surely 200 must be less than 10% of all the students. And they calculated their standard deviation. Now, what are we going to do with this information? What can we say about the difference between the two schools' sample proportions? Well, something, I'm sure of it. What if we showed a simulated sampling distribution of the difference in the sample proportions? We did something like this way back in the day where we made that simulated difference of the John and Jen resume ratings. So this is a similar idea. But you'll notice here is they've highlighted that one little red dot there. So one set of samples gave p hat 1 of 0.72 and p hat 2 of 0.47, and when they subtracted them in p1 minus p2 order, they got a difference of 0.25. So that's where this one little red dot came from in the simulation. But I'm sure you've noticed there's a whole lot of dots here. So this is a collection of so many simulations. Now the other thing that I want to point out to you is smack dab in the middle here, we have a difference of 0.2, which happens to be the mean. Well, think about it this way. The first school, I believe, was 0.7, and the second school was 0.5. I might have got those backwards. No, I didn't, because that's the order they're subtracting them. So if I took P1 minus P2, that would be the overall mean for our sampling distribution. Just like earlier, just whatever the value for P was, was your mean. Well, when I'm taking the difference, I'm just going to subtract them. Makes logical sense. Now the standard deviation is where it gets weird. I think it was chapter 6 we did this in, but remember when we're calculating standard deviation with two different, oh gosh, my brain is not firing today. Anyways, we got two different distributions we're trying to combine together here in a subtraction problem. Remember, we were kind of like, oh my gosh, what's happening? Because we don't subtract their variances, we actually added their variances together. So variance, square rooted, life is good. All right, so that's how they're going to calculate the standard deviation. The good news is you don't have to remember that formula. That's going to be given to you. All right, so what did we just find out? Well, if we have a sampling distribution where we're trying to find the difference between two proportions, then the sampling distribution is approximately normal if you can check the large counts, and it has to happen for both of the populations. So that's kind of annoying because you got to do twice the work. The mean of the sampling distribution is simply going to be the difference between the two p-values from the populations. All right, makes sense. Make sure you go in the right order. That's important. The standard deviation, of course, is strange. You still have to check the 10% rule, which I just love how they check it. They're just like, assume it's true. But remember, when we're doing the combination of the variances, we don't subtract them. We add them and then square root. We kind of went over that back in chapter 6. That was complicated, I know. Again, you don't have to have that memorized. That's the good news. Now, there's a big note here. Note that the formula for standard deviation is exactly correct only when we have two types of independence. So we have to have independent samples so that we can add the variances of P1, P hat 1 and P hat 2. And we have to have independent observations within each sample. So when sampling without replacement, the actual value of the standard deviation is smaller than the formula suggests, but because we're satisfying the 10% condition, the difference is so negligible that they just don't worry about it. It just makes your math easier. So that's why we keep inferring that you have to say the 10% condition is met. That allows you to use these nice formulas. And believe it or not, those are nice formulas. Oh, I love this question because it's about goldfish. So let's say we have 2 bags of goldfish, the kind that have, purple, red, orange, all those good ones. So bag 1 has 25% red and bag 2 has 35% red. I guess you busted open the bags of goldfish and counted. Each bag contains more than 1,000 crackers. Using a paper cup, your teacher takes a simple random sample of 50 crackers from bag 1 and a different sample of 40 crackers from bag 2. And they would like you to define P hat 1 minus P hat 2 to be the difference in the sample proportions of red crackers. Now, again, bag 1 is subscript of 1 and bag 2 is subscript of 2. So the first question is, what's the shape? So we're supposed to be checking whether we can use the normal, if this is approximately normally distributed. So we need to check the large counts rule for everything. Whew, all right. So in bag 1, which I forgot what I had already. So 25% red, and it was sample size of 50. So 50 times 0.25 is 12.5. So you should expect to get 12.5 red fish in your bag 1 sample. And then you should expect to get 37.5 red fish in, no, I'm sorry, not red fish in bag 1. So either way, both of those are greater than 10, so check, check. And then we do the same thing for bag 2. So this was a sample size of 40 times 0.35. So there's going to be 14 red fish, supposedly, in our sample for bag 2. And then 26 not red fish in bag 2. Anyways, all of them are greater than or equal to 10, and that satisfies the large counts condition. So because we satisfied the large counts condition, we can say this is approximately normal. That's what they're looking for. Is it annoying to have to do all that? Yes, it is. I'm so sorry. All right, so now they want me to find the mean of the sampling distribution. So remember, the mean is determined by the order in which they subtract them here. So p hat 1 minus p hat 2 means that we're going to take p1, which is 0.25, minus p2, which is 0.35, and order does matter. So you actually get a mean value of negative 0.1. Calculate and interpret the standard deviation. Well, first thing they should do is check the 10% rule. So because, and you got to check it for both bags, 50 is less than 10% of all the crackers in bag 1, and 40 is less than 10% of all the crackers in bag 2. How do I know that? Because earlier they said something like each bag has more than 1,000 crackers. So, this is assuming the bag's at least 500, and this is assuming the bag's at least 400, which it is. Okay, anywho, 10% rule, check. That means we can use this weird formula where we take bag 1's variance, kind of. I keep saying variance. It's a portion of the variance, isn't it? Abruzzo, you're doing a bad job with words today. And then same thing with bag 2. We add them together before we square root. And we find a standard deviation for the difference in sample proportions to be 0.0971. So here comes that fun thing, except this time now we have to add this context of the difference in what order. So the difference, bag 1 minus bag 2, in the sample proportions of, here's context, red goldfish crackers, here's the thing that always shows up, typically varies by about 0.097, and then always from the true, this time it's difference in proportions of negative 0.10. Yikes. We're going to have another poster for that, kids. Ooh. And of course, there's a part D. Estimate the probability that the proportion of red crackers in the sample from bag 1 is greater than the sample from bag 2. Now, they're going to be a little crafty in how they set up this normal distribution. So when they write it in inequality notation, it says the probability that p hat 1 is greater than p hat 2. But that's not something we can do on our calculator, So they got to rearrange it so that it has something to do with 0, or at least the difference in proportions. So what they did is they subtracted the p hat 2 over, and they got p hat 1 minus p hat 2 has to be greater than 0. Well, this is perfect. This is something that we can do normal distribution calculations on. So of course they give you options. You can do the z-score fun, which everybody loves a z-score, right? So 0, by the way, is your x bar, right? So 0 minus the mean divided by the standard deviation if you're finding z-scores. But, back up. Since I never find, and you know what? They didn't show the thing that I would have done because I'm lazy. I would have done normal CDF with, let's say they want greater than 0. So I would have said lower bound. Oh yeah, they did. This is exactly what lazy Abruzzo would have done. I'll be honest though, they always go with 1,000 for like a gigantic upper bound, which is plenty big. I'm like a crazy lady who just puts a bunch of 9s. So you would have seen my work say lower 0, upper 99999, mean negative 0.10, standard deviation of 0.0971. So whether you did z-score using table A or you did normal CDF, standardized or unstandardized, you should get a probability value of approximately 15%. So we know it's not going to be exact every time. That was a hoot. I feel like we need some more examples of that because that is tricky. But what's really cool is we're setting ourselves up so nicely for the next chapter, which is going to be our introduction to inference. And I think we're going to get to a moment where everything kind of comes together and you're going to be so happy. I know I am. All right. Good luck, everybody.